Hello. Today I'll be speaking about open source video processing pipelines. It's a huge topic, way too large to cover in this 19-minute video. If you'd like to know more, then I invite you to read wiki.pythonlinks.info. It's searchable. Here's a QR code you can scan to visit the site, wiki.pythonlinks.info. So here we have a completely open source video processing pipelines. It's called the frame glasses. They have a camera, an FPGA, a display on the lens. They have a microcontroller with Bluetooth. The way it works is the camera takes a photograph, it sends it through the camera pipeline to the microcontroller, to the cloud where AI recognizes it. It sends the results back to the microcontroller over Bluetooth. That sends it to FPGA through the display pipeline, and that gets displayed on the lenses. Here we have a more detailed view of the camera pipeline. There's a camera on the left-hand side. It sends a signal over MIPI DPHY to the FPGA that takes the individual bytes and converts them into pixels. That gets debayered, it gets cropped, it gets compressed with JPEG compression, saved to memory, and then over SPI sent off to the microcontroller, which uses Bluetooth to send it off to the cloud. It's completely open source, all except for the manufacturing technology, which is really a pretty critical piece. Most of these video processing pipelines are a mixture of open source and closed source components. So I'm currently working with drone video pipelines. There's a camera, MIPI interface, there's compression, encryption, IQ encoding, goes to radio, gets transmitted, received, decoded, decrypted, decompressed, and displayed. So MIPI is well known, but it turns out that it's proprietary. You have to pay money just to read the spec, and if you're using MIPI, then somewhere along the way you're paying a licensing fee to the group. DV-HDMI is a little bit more confusing. DVI is open source, you're free to use it. HDMI is a superset of DVI. It adds sound into the frame around the image. And so HDMI is closed source, and the lawyers are very careful to make it very opaque where the boundary is between one and the other. So if you're doing that stuff, you need to be careful you're not violating their license terms. For connecting the drone to the ground station, they're completely open source solutions. Here's the RunCam Wi-Fi Link 2. It takes DVI out of a camera and transmits it over a version of Wi-Fi to the ground. It has very low latency. What it does, it doesn't do error checking, and so that makes the signal, gets the signal delivered much faster. Completely open source case, completely open source circuit board, and all the software is also open source. You can do with it whatever you want to. If you want to do something more complex and you can't do it with a microcontroller based, then you need a field programmable gateway. They're more sophisticated chips with higher bandwidth. So there's Blade RF, which is again completely open source, circuit board, Verilog, VHD actually, but the programming language. Completely open source, do with it what you want. More typically, when we think of cameras, historically we think of something like the camera on the left. Nowadays people talk about cell phone cameras. They have multiple lenses. Maybe they have a distance sensor in there, depth sensor. They can have different exposure times, they can have different focal distances, and they can all be merged in real time into a video at 60 frames per second. Just amazing technology. But engineers tend to think of something more like a Raspberry Pi camera. So it's really an image sensor that you connect to a circuit board. For about 50 euros, you can get a Raspberry Pi 12 megapixel camera. Just amazing. And then you can plug that into a Raspberry Pi Zero, $10 for a single core, $15 gets you 4 cores. It's got a USB 2 port, it's got MIPI CSI, it has compression software and a little GPU, DVI output, and it can also transmit the image over a parallel RGB using the Raspberry Pi form factor pins. Amazing how much you get for so little money. You may have studied lenses. Here's a very simple lens. But they've gotten, like everything else in the pipeline, they've gotten much more complex. So here's a 2016 iPhone lens patent. There's also a tremendous variety in the image sensors. The wiki links to an image sensor database. It has 874 image sensors, probably has more by now, and it doesn't even include a number of different image sensor vendors, which I found listed at the bottom of this page. What do you do with all of that? Well, people build camera stacks. Here we have the ArduCam USB shield. At the top there's a lens. Below that there's an image sensor board. The bottom board is USB 2 or USB 3 with compression. And then in between you have a camera adapter board. And the issue is there are so many different camera protocols that you need a whole bunch of different camera adapter boards. So it's not the only camera stack out there. ReCamera is a completely open source camera stack. It has this beautiful metal case. It has to be a metal case because the middle board is a microcontroller. It could be like a RISC-V board, and it generates a lot of heat, and so it needs the metal case. But I like it. It looks great. And you can also see in the bottom right, it's got this little robot arm, so you can control which direction it's going. Looks quite cute. What do we do with these camera stacks? Well, the wiki has some 24 different processes that run on camera stacks. Defective pixel correction is one of the first ones you may run into. So if it's a short circuit on a black background, you're going to get a white dot. If it's a open circuit on a white background, you're going to get a black dot. So those need to be corrected. You can do pixel binning. The Raspberry Pi camera I mentioned has 12 megapixels. My desktop monitor has 1.4 megapixels. So we can shrink down the resolution, basically average in adjacent image sensor values, and you reduce it by a quarter. Historically, people used bare filters. These would actually triple the size of the data. The image sensors used to be the same size as the displays, and so what they wanted was for every single color pixel, they wanted to turn that into a 3-color pixel by averaging with adjacent ones. And so Wikipedia has a great detailed description of how all of this works. So it triples the data size as opposed to the pixel binning reduces it by a quarter. You also have to be aware of camera spectral responses. The camera has a response, the display has a response, the human eye has a response, and they're all different. So if you look at this woman's face on the left-hand side, she looks like a zombie. For evolutionary reasons, we're very careful. We're very sensitive to people's skin color being off. We need to know if they're sick. But we don't really care if the background green is correct or not. So what you need to do is we need to rotate the color vectors, and then her skin looks perfectly normal. You may also want to do video cropping, or if it's a high resolution image, that's effectively digital zoom. On the desktop, it's really easy because you don't really care what size the resulting image is. In real-time systems, often you want the image to cover the entire display, and so you have to scale it some. So it's a bit more complicated, and you also have to get the timing right, but all quite doable. Here we have JPEG compression. What it does is it takes an image and it represents it as a sum of a few of these 64 different options. So in the upper left-hand side, if it's all a single color, you'll get white for it. All the way to the bottom right, you have this 8x8 grid. So typically, for some 64 pixels, it'll convert each color into 4 or 5 JPEG values that get added together, scaled and added together. We also have the whole issue of displays, a large number of different display options, some simpler, some more complex. Often people do DVI or HDMI out, so you may want to actually display it on a computer. So these lovely DVI to USB 3 dongles, make sure you get the USB 3 and not the USB 2 version, less than $10. The way they work is they have a double frame buffer inside. So the HDMI signal comes in, it gets written to one frame buffer. In the meantime, USB 3 is reading from the other frame buffer. When the frame is done, they swap. USB 3 reads the new frame buffer, and HDMI writes to the old frame buffer. That's great, but it takes twice as much memory, and microcontrollers don't have much memory. So what do you do if you want to use a microcontroller? I recommend libmpix on Zephyr OS. What that does is it uses a ring buffer. So a pixel comes in, it gets written to one end of a ring buffer. When it needs to go out, it gets read from the other end of the ring buffer, and the unused cycles, the CPU can operate on those pixels, do some calculations on them. And in particular, many microcontrollers have some parallel single instruction and multiple data options. And so you can do actually vector operations on it. And so you can get a lot more computation done in a particular amount of time. These are basically for low bandwidth applications. If you have a high bandwidth application, so here we have a fisheye undistort in real time. You can imagine that this is some computational complexity to do this. You really need an FPGA, and of course an open source FPGA is what I recommend. When we say open source, we don't mean that the chip itself is open source. They're all proprietary. What we mean is that the tools that create the circuitry are open source. So you have Yosis, which does synthesis of Verilog into a particular netlist, and then XPNR, which places and routes that netlist onto the FPGA. What's an FPGA? A simple answer is it's a circuit that's very good for processing videos. There are a number of different FPGAs which are supported by Yosis. The one you may want to look at first is Lattice NX17 or 40. They have 2.5 gigabits per second MIPI hardcores. So that's a good bandwidth for getting your image in. I'm working with the 54 euro European Olimex GateMate board. GateMate has this very interesting 5 gigabits per second SerDes, serial and serializer, deserializer SerDes. And so that's a lot of bandwidth. I'm working to connect it to a PCI Express. You can plug a Waveshare OV5640 camera into these. They give you 5 megapixels. The fisheye version is only $16. If you use a rectilinear camera, it's more expensive because it needs autofocus. At 90 megahertz, 60 frames per second, you could do 1.5 megapixels. But because these cameras have image compression, JPEG image compression, you can actually do much larger images than that. Very cool. Here we have the $79 IcePi Zero. It should be shipping in January. It has the same form factor as the Raspberry Pi, and so you can do MIPI into the Raspberry Pi Zero and then do a parallel interface into the FPGA, and then the FPGA has a DVI output. There's also a need for these open source tools in farming. Open source ecology.com has a whole bunch of farming equipment. They're starting to move into construction equipment also. They're very ugly, but you can modify them, do whatever you need with these machines. And what they need is photosynthesis spectrum measurements. So plants, when they're healthy, give off a very strong photosynthesis spectrum. You can actually measure the health of the plants by flying over with a drone and measuring the spectrum. Actually, they do this in Poland, and that determines how much the farmers get paid. So the group I spoke to is using the DJI multispectral camera. You can see the RGB and infrared lenses on the top, navigation lenses on the bottom, and it has some nominal frequencies that it measures, but they're not the peaks and valleys of the photosynthesis spectrum. So ideally you'd like to be measuring the peaks and valleys with a camera that's dedicated to photosynthesis, ideally an open source one. Particularly with climate change and increasing food prices, whatever we can do to help farmers is really very needed. So what are some of the recommendations? If you have a shrink-wrapped application that does what you need to, just use it. That's the simplest solution. For low bandwidth applications, you can use libmpix on Zephyr OS on a microcontroller. For higher bandwidth applications, you need an FPGA. You can use a Raspberry Pi MIPI CSI to DVP on any FPGA. That'll give you 1.5 gigabits per second. For up to 2.5 gigabits per second, you'd probably want to use a Lattice NX17, maybe closer as 33 or 40 with MIPI CSI. If you need a European FPGA, use GateMate. It has a 5 gigabits per second SerDes, and I'm working to connect that to a 4 gigabit per second PCIe Express out. If you need higher bandwidth, then you have to go to a closed source FPGA. Often people need cables attached to their cameras. So for example, in the automobile or trucking industry, you'll have a camera or LiDAR at one end of the vehicle and you need to run a cable to the other end of the vehicle. If it's less than 3 meters, you can do USB 3. Lattice NX33 actually includes a USB 3 port. Less than 5 meters, you can do USB 2 with H.264 compression. Less than 15 meters, there are a whole bunch of solutions listed on the wiki. MIPI A-PHY is probably a good choice. How did I get into this? Well, I presented at the Chemnitz Open Source Hardware Conference, and they gave me the opportunity to write an article. I wrote a 10-page article, but it was just overflowing with content. So I created a wiki, and just content keeps getting added to the wiki. Wiki.pythonlinks.info, and it's got search now so that you can find whatever it is you're interested in. People really like it. Venkat said, that's a lot of good work condensed into the wiki. Good work. Joshua said, it looks nice to organize a bit like a series of chests in a gold mine because the content in there is really valuable if you're working in this industry. Simon said, by the way, Christopher Lozinski, I've been reading through your Python Links site. It's fascinating. So lots of good content there. If you have any questions, feel free to contact me on open source Mastodon at pythonlinks@mastodon.social, pythonlinks@mastodon.social. You can send me an email, lozinski@pythonlinks.info, lozinski@pythonlinks.info, or you can visit the wiki, wiki.pythonlinks.info, wiki.pythonlinks.info. Here's a QR code for the wiki. Thank you so much.